Good morning. Is the audio clear? Good morning. Let us start the subject then. Yesterday, if you remember, we were discussing the concept of momentum equation. We have seen the concept of impact of jets also. Yesterday, we have covered the concept of impact of jets. Impact of jets. Today, we are going to start the last topic of this chapter. Let me write the date first of all. Today, we are going to start a topic known as moment of momentum equation. Moment of momentum equation. Moment of momentum equation. This is a topic we had to discuss today. Let us start then. Imagine you're having a nozzle. You're having a nozzle. Through this nozzle, there is some fluid coming out. There is some fluid coming out with a velocity v. Imagine the nozzle is something like this. When the fluid is coming out with a velocity v over here, the nozzle is going to get a push. It is going to get some kind of a force in this particular direction. We know that the value of force over here has to be equal to m dot times velocity. The force over here has to be equal to m dot times velocity. Yesterday I have discussed this thing. Okay. Now let us say I am integrating this nozzle with a lever. I'm integrating this nozzle with some lever over here. Suppose I have a lever over here hinged at this particular point such that the distance over here is equal to certain distance r. The distance is equal to certain distance r. So now I'm going to have this particular point. Let us say this point is point O. Now what happens about this point O? There is going to be certain moment created, certain torque created. The value of torque created over here has to be equal to, it has to be equal to force times R, which implies the value of torque over here is equal to force, which is equal to m dot v times R. This equation over here, m dot into v into R, this term over here is known as your moment of momentum equation. It is known as moment of momentum equation. So I can say moment of momentum, moment of momentum, moment of momentum gives torque, or you can say moment, torque or moment. Moment of momentum is going to result in torque or moment. Now the question is, how to analyze this moment of momentum? Okay. For this purpose, we are going to take a standard problem which has appeared in examinations in GATE as well as in IS examination, which is known as lawn sprinkler problem. Let us take an example of a lawn sprinkler. Example of lawn sprinkler. Example of lawn sprinkler, let us say. Now we know that if you might have seen in huge gardens, in very big gardens, there are some kind of sprinklers. A 3D diagram of the sprinkler could be something like this. there are some sprinklers which are something like this. The fluid is entering into the sprinkler from the ground. The fluid enters from the ground. It gets divided into two portions. So what happens? The fluid comes out in this particular manner. When the fluid comes out this way, the sprinkler, by the virtue of momentum, that recoil is going to be there. This sprinkler is going to experience some kind of rotation over here. So imagine this over here is a sprinkler. This is a hinge over here in middle. From the bottom, water is entering. Okay. Some fluid is moving in the direction which is perpendicular to the screen outward. Some fluid is moving into the screen. So now what happens automatically? The sprinkler starts to rotate now by the virtue of momentum conservation. Okay, so now what we are going to do is we are going to look at this is a rough 3D diagram of the sprinkler. What we are going to do is we are going to look at the top view of this particular sprinkler. Let us see. I am looking at top view of sprinkler. A sprinkler can have any number of nozzles. Over here, I have taken only two. You can have three also. But mostly in examination, we are only having sprinklers with two nozzles only. Let us see. I look at the top view of the sprinkler. Imagine the top view looks something like this. This is the top view. This, let us say, is the point of hinge. This point is some point O. Point of edge, point O. Let us say this is my nozzle, nozzle 1. This is my nozzle, nozzle 2 over here. From this nozzle 1, the fluid is going to come out with certain velocity. Let us say that velocity is velocity V1. From the nozzle 2, the fluid is going to come out with certain velocity. Let us say that velocity over here is velocity V2. This V1 and V2 are velocities of fluid from nozzle. Let us say because of this velocities, the sprinkler is experiencing some angular motion over here. It is experiencing some angular motion. Please listen carefully. It is very simple. Okay, the problem is this topic is not discussed almost in any book. Very few books have discussed this topic, and that too in detail. Very few books have discussed. So try to understand it over here itself. It is very logical. First thing, you see, look at the first thing I have shown. The fluid is coming out. Now, by the virtue of fluid coming out, what will happen? By the virtue of fluid coming out, you are going to have some kind of motion of this thing. Why in this particular direction? Imagine that as the fluid comes out over here, nozzle tries to move down. Over here, nozzle tries to move up. The only kind of rotation possible is this anti-clockwise rotation. Let us say the angular velocity over here is equal to omega. Omega is the angular velocity of this anti-clockwise rotation. Okay, accepted. Now, by the virtue of this omega, what happens? Let us say this distance over here is R1. This distance is R1. This distance over here is R2. The distance here is R2. Now, what happens? The nozzle, this nozzle 1 is going to develop certain velocity. I'm going to represent the velocity of nozzle with the letter U over here. Suppose U1 is the velocity of nozzle. Likewise, over here, I'm having certain velocity of nozzle. This velocity of nozzle is equal to U2, let us say. This velocity of nozzle is equal to U2. So I'm having certain velocity U2 over here. So what are U1 and U2? U1 and U2 are velocities of nozzle. Velocities of nozzles, corresponding nozzles. What should the value of u1 be equal to? The value of u1 from basic mechanics, we know that if you are having angular velocity omega and certain radius, then the value of velocity has to be equal to radius times omega. Similarly, what should the value of u2 over here be equal to? What should the value of u2 be equal to? Let me write u2 over here. u2 should be equal to r2 into omega. u2 is, once again, r2 into omega. One minute, please. This over here is top view. Okay. So now I'm having two velocities defined. One is the velocity of liquid coming out, which is represented by V1. The other is the velocity of the fluid of the nozzle itself. That velocity over here is known as, let us say, that velocity over here is represented by u1, the velocity of the nozzle itself, and u2 for nozzle 2. Now what will happen when the fluid is coming out with V1 and the nozzle is moving back over here? The fluid is going to develop. Listen to this carefully. When the fluid is coming out with V1 and the nozzle is going down over here or moving downward over here with U1, the fluid is going to develop a relative velocity. So let us see, the fluid develops a relative velocity. Similarly, over here, the fluid is developing a relative velocity. Remember, always show relative velocity. Always show relative velocity in the direction of velocity of fluid itself. So since V1 is upward, I'm showing relative velocity upward. Since V2 is downward, I'm showing relative velocity downward. Let us say these relative velocities are represented by VR1 and over here by VR2. Relative velocities are represented by VR1 and VR2. So what are these VR and VR2? VR1 and VR2 over here are the relative velocities. Relative velocities of the fluid. With respect to whom? With respect to nozzle. With respect to nozzle. VR1 and VR2 over here are the relative velocities of the fluid with respect to the nozzle. What should the value of VR1 be equal to? Think logically. VR1 value should be equal to how much? You see over here, I'm having some velocity upward. I'm having this velocity downward. Strictly speaking, the value of VR1, the value of VR1 vector has to be equal to V1 vector minus U1 vector. Please understand this thing. Whenever you are having both in the opposite direction, then this U1 itself is negative. So what will happen then? They will both add up. When in the opposite direction, they will both add up. So this value actually has to become equal to VR1 value has to be equal to how much? It has to be equal to V1 minus, then this itself is negative. Therefore minus U1. What will it eventually become? It eventually, one second, let me create some space over here. One moment, please. What will it eventually become? The value of VR1 eventually becomes equal to, this becomes equal to V1 plus U1. The value of VR1 eventually becomes equal to V1 plus U1. Similarly, now you try. Similarly, what should the value of VR2 be equal to? Again, it should be equal to V2 vector minus U2 vector. Now you see both of them are in opposite direction. So if V2 vector I'm taking down, U2 vector is negative of U2 in downward direction. Therefore, again, this becomes equal to how much? V2 plus U2. V2 plus U2. If you are still having any confusion, just remember, this is a concept of relative motion you have studied in your 11th class. If you still have a doubt, just remember, if these two are opposite, they will add. If these two are in the same direction, they will subtract. You will see both the cases. I'll take two problems. In one problem, you'll be seeing both of them in opposite direction. In one problem, you'll be seeing both of them in same direction. Okay. This is regarding the velocities. Again, I'm mentioning there are three velocities we are supposed to mention over here. The first velocity is the absolute velocity with which the fluid is coming out. That is represented by V. The second velocity is the nozzle itself is going to have certain velocity. That velocity is u. And the third velocity is the relative of these two, first two velocities. That is v and u are going to have certain relative velocity. V and u are going to have certain relative velocity. That is the third velocity represented by VR1 and VR2 over here. This is the concept in here. Now, listen to me carefully. Whatever is the fluid coming out of this thing, that is going to have some discharge. No? Fluid is going to have some discharge. Let us say that discharge is equal to Q1. Discharge is equal to Q1. This Q1 value has to be equal to how much? Q1 is the discharge coming out of nozzle 1. What is the value of Q1 equal to? Let us say the cross-section area over here is A1 multiplied to which velocity? Remember always, whenever in these particular cases you are going to observe, the discharge should be always corresponding to relative velocity. So A1 multiplied to VR1. Similarly, the value of Q2 will be equal to how much? If the cross-section area over here is A2, it has to multiply to which velocity? VR2. I'm going to write that note in the next page actually. I don't have space over here. That note, listen to the note. The discharge is supposed to be corresponding to which velocity? It is supposed to be corresponding to the relative velocity of the fluid emerging out from the nozzle. So I'm going to the next slide now. This says, the note over here says, the note says that the discharge corresponds to the relative velocity corresponds to the relative velocity. Remember this rule. Now you might have a doubt, why is the discharge not A1 V1 or A2 V2? Why is it A1 VR1, likewise A2 VR2? Why are you having relative velocity over here important? I'll clarify that doubt. Now imagine that I'm drawing a line diagram now. Imagine that this is point O, this is some point 1 over here. I'm having velocity V1 in this particular direction. And now this nozzle in 1 unit time, let us say this nozzle has come down to here in 1 unit time. Okay, let us say this is representing U1. This is representing U1. Now, when this nozzle, please understand, the nozzle was initially over here, later the nozzle came over here. So basically, in 1 unit time, the jet is going to have how much length? The fluid is going up, nozzle is going down. That means the fluid is going to have this much length in 1 unit time. The fluid is going to have this much length in 1 unit time. Now, this much length over here corresponds to which velocity? It corresponds to VR1 velocity. Please understand this thing. As the fluid is going up, nozzle is going down, entire length from here to here is going to be filled with the fluid. The corresponding velocity is VR1, and the discharge over here should correspond to this velocity. Therefore, the value of discharge should be corresponding to V relative velocity only over here. ठीक है, चलिए. With all these things, let us start a question. From the question, you will understand everything. If you are still having any doubts, please wait for the question to finish. I hope that you'll be understanding from the question itself. Let us take a problem. This problem is worth 2 marks in GATE examination. From this topic, 1 mark questions are not that much possible. Mostly 2 mark questions only can appear. Okay. So the question is something like this. The question says, let me draw a nozzle for a sprinkler first of all. Suppose you are having some sprinkler. This is a top view of a sprinkler. A top view of a sprinkler is given. Let us say I have hinged the sprinkler somewhere over here. Let me call this point as some point O. This nozzle is nozzle 1. This nozzle is nozzle 2. Suppose this radius over here is R1 and this radius over here is R2. This radius over here is R2. Let us say that the net discharge entering into this assembly is equal to some 3 liters per second. Half the discharge is going over here. Let us say the discharge going over here is equal to Q by 2, and half the discharge is going on into this thing. Let us say this is Q by 2. The value of R1 is equal to 0.3 meters. The value of R2 is equal to 0.8 meters. R and R2 are given to you. Okay. The cross-section area at nozzle 1, this cross-section area is equal to the cross-section area at nozzle 2. Let us say it is equal to 1.5 centimeter square. Water is a fluid, so density over here is equal to 1000 kg per meter cube. 1000 kg per meter cube. After all this data is given to you, the question says that if this is rotating in this direction, the question says, 1 second, 1 moment please. The question over here says that find the value of omega if the net torque is 0. Net torque is 0. Net torque at which point? At point O. The net torque is equal to 0. If the net torque is equal to 0, you are supposed to find the value of omega. This kind of question can appear in your GATE examination. It is worth 2 marks. This is worth 2 marks. Okay. Now to solve this question, I'm going to take 3 steps over here. Very simple. 3 steps. The first step is to draw this particular diagram of velocities. I'm supposed to draw the diagram of velocities. Okay. Recall how many velocities we are going to have. 1 moment. Recall how many velocities we are going to have. We are going to have in total 3 velocities. One is the velocity of the fluid. The other is the velocity of the nozzle. Third is the relative velocity, which is the most important velocity. So, let us do one thing. Let us draw like a line diagram over here. I'm using a line diagram to show this thing. Imagine that this entire line over here is representing this entire launch sprinkler. Okay. I'm choosing a point. This point is some point O. This point over here is some point 1, and this point over here is some point 2. At point 1, the fluid is coming upward with certain velocity. The velocity of the fluid coming up is equal to V1. The velocity is V1. Similarly, at point 2, the fluid is coming out with certain velocity. That velocity, let us say, is equal to V2. Okay. First velocity shown. Second velocity. Look at the sequence. Second velocities. I know that this is rotating in this direction. In this direction. If it is rotating in this direction, then the nozzle itself is going to have some velocity. Now you see, this direction is going to create a velocity in this direction. This is u1. The value of u1 has to be equal to r1 into omega. R1 is, 1 second, 0.8 is v2 high for this. Let's say 0.5 over here for r2. Yes. The value of u1, let us say, is equal to r1 into omega. R1 over here is 0.3 into omega. Therefore, same is rotating like this. Point 2 is going to have velocity upward. Let us say the velocity is upward over here. This velocity, let us say, is u2. U2 over here has to be equal to r2 into omega. That is equal to how much? 0.5 omega. This is u2 over here. I have shown the second velocity also. I have shown the second velocity also. The next velocity is the most important of velocities. The next velocity is the most important, which is relative velocity. I told you, first of all, show the arrow. Show the arrow. Wherever you are seeing V, in that direction you show the arrow. So V over here, I'm showing the arrow over here. Now, this is relative velocity. Let us write, this is relative velocity, VR1. What is the value of VR1 equal to? I told you, when they are opposite, just add them. They are opposite over here. That is V1 plus 0.3 omega. And V2, VR2 over here, VR2 over here has to be equal to, again, opposite. So V2 plus 0.5 omega. V2 is 0.5. First part of the solution is done. All you have to do is just draw this kind of line diagram, which is representing the velocities throughout. Okay. Now from these velocities, try to develop the equation of V1 and V2. Try to develop the equation of V1 and V2 because you will require V1 and V2 sometime later on. Now look over here. If VR1 is equal to V1 plus 0.3 omega, then V1 will be equal to how much? VR1 minus 0.3 omega. VR1 minus 0.3 omega. Similarly, over here you observe, if VR2 is equal to V2 plus 0.5 omega, V2 will be equal to how much? It will be equal to VR2 minus 0.5 omega. This is the value you're going to have. So V1 and V2 are known over here. Okay, fine. First part is finished. Now, second part over here. Second part over here is to develop the value of VR1 and VR2 from discharge concept. We know that the value of discharge has to be equal to area multiplied to which velocity I told you. The discharge corresponds to which velocity? Relative velocity. The reason is jet length is not corresponding to V1 or V2. Jet length is corresponding to VR1. Okay. So over here I'll write VR. Now tell me, if net discharge entering into the assembly is equal to 3 liters per second and the discharge going over here is equal to 3 by 2, that is 1.5 liters per second. So I can write from here. That 1.5 liter per second. 1.5 liter per second means 1.5 into 10 power of minus 3 has to be equal to A1 is 1.5 centimeters square. 1.5 into 10 power of minus 4 meters square multiplied to VR1. Multiplied to VR1. Okay. This This is Q1, this is A1, this is VR1. This implies the value of VR1 has to be equal to how much? The value of VR1 has to be equal to this divided by this. You are going to get 10 meters per second. Similarly, Q2 is equal to A2 into VR2. Q2 is equal to A2 into VR2, which implies Q2 is also equal to 1.5 into 10 power of minus 3. A2 is also equal to 1.5 into 10 power of minus 4. VR2 is VR2 over here. So from here it implies that the value of VR2 is also equal to how much? 10 meters per second. The value of VR2 is also equal to 10 meters per second. Okay. So once we are having the value of VR1 and VR2, now this first step was just line diagram. Second step is this thing. Last step now, the equation of torque. I see over here I'm having two nozzles. I see two nozzles. I'll write net torque is equal to two nozzles. Therefore, torque 1 plus torque 2. Since I'm having two nozzles, I'm writing torque 1 plus torque 2 over here. Okay. So now, how much is torque 1? We know that net torque is equal to 0. Already given to me in the question, net torque is equal to 0. Torque 1 is equal to how much? Torque 1 is equal to m dot into V1 into R1. Torque 2 is equal to how much? M dot into V2 to R2. You see, I have added them. The reason is both of them are facing in the same rotational direction. Look over here. Please observe. With respect to point O, this direction of rotation is clockwise. With respect to point O, this direction of rotation is clockwise. Since both of them are having same direction of rotation with respect to point O, therefore I'm adding them. Okay, fine. Now I can write this implies m dot 1 and m dot 2 should be there. M dot 1 into V1 into R1 has to be equal to negative of m dot 2 into V2 into R2. Now, if you observe, since the value of discharge 1 and discharge 2, both of them are same. Discharge 1 and discharge 2, both of them are same. What will happen over here? M dot 1 and m dot 2 should get cancelled off. M dot 1 and m dot 2 got cancelled off. Now what to do further? I have V1 and R1. I know the value of R1. R1 is 0.3, R2 is 0.5. What about the value of V1 and V2? This first step was actually for V1 and V2 only. You see, first step V1 is VR1 minus 0.3 omega. That is 10 minus 0.3 omega. So I'll write over here. This implies 10 minus 0.3 omega. This is V1 now. Multiplied to 0.3. This is R1 now. Has to be equal to negative of this negative as it is. V2 is equal to how much? 10 minus 0.5 into omega multiplied to 0.5. 10 minus 0.5 into omega multiplied to 0.5. Now what does this imply? This implies 3 minus 0.09 omega has to be equal to, minus 5 plus 0.25 omega. From here it implies that 8 is equal to 0.34 omega, which implies omega is equal to 8 divided by 0.34. Everything is in SI units, therefore radian per second. You can give me the value of omega from here. 0.34 is as good as almost 0.3333. That is as good as multiplying by 3. Nearly 24 you should get as answer. 23.53 is the answer. So the value over here is 23.53 radian per second. 23.53 radian per second. M dot got cancelled because m dot over here is equal to rho into q1. In the question, you see the value of q1 and q2, both of them are same. That is why m dot got cancelled off. Okay. Now, if you observe this problem, look carefully over here. If you find in literature some books, you might not find the exact same methodology, but I'm following this methodology because this is easier to understand. Okay. If you observe, the ultimate aim is to write down, please stop commenting for some time and listen. The ultimate aim is to write this particular equation. Okay. If I start with this equation, I'll have many unknowns. For example, V1 is unknown, V2 is unknown. So what I'm doing, I'm actually starting with this line diagram. From this line diagram, I'll develop the equation of V1 and V2. I'll develop the equation of V1 and V2. Once I develop the equation of V1 and V2 from the line diagram, then I will find out the value of VR and VR1 and VR2 because V1 and V2 are depending on VR1 and VR2. Once I got all these things, then my problem is actually starting from here. Problem is only this big. It is starting from here. Then I'm going to write the equation of torque. Okay. Once I write the equation of torque, the only thing unknown over here comes out to be omega. I can then find out the value of omega. Okay. Now, if you want to know whether you have understood this or not, then the best way is to try a problem. This problem I have done. You're not having many problems to practice in this thing. So this problem I have done. If it is not mentioned Q1 is equal to Q2, then you have to correspondingly write the value of m dot 1 and m dot 2. For example, let us say, very good question. For example, let us say, if Q1 value is equal to some 3 and Q2 value is equal to some 4, then you'll write over here rho into 3 and rho into 4. Likewise, and then again you'll get the same kind of something similar only. Okay. The third step over here is the equation of torque. And someone is asking what is the meaning of net torque is equal to 0. Net torque over here equal to 0 means at this particular point, hinge point, you are having free rotation without any resistance, without any friction. You are having some free rotation taking place. Okay. See, to imagine this rotational torque at the hinge, you try to imagine when you're opening some doors which are already having some kind of rust at the hinges, you will find that there is some resisting moment. It will create some kind of sound also. That resisting moment over there is a frictional torque or resisting torque at this particular point. That value is set to be 0 at this particular point. Okay, the value over here is equal to 0. That means the rotation right now is free rotation. Just by the virtue of fluid coming out, this nozzle is entering into rotation. It is not having any torque over there. U is considered in the equation. See, when I'm writing V1, inside V1, U is there. U is considered in the equation. So let us start a problem now. Let us start a problem. Imagine the top view of the nozzles is something like this. Look at this case. Imagine you are having a problem something like this. This appeared in gate examination. Okay. This was a slightly tricky case where both the nozzles were facing in the same direction. both the nozzles are facing in same direction, upward direction only. Let us say you're having a hinge over here. I'm going to take the same data. The data I'm taking is same. Let us say this is R1. The value of R1 I'm taking is equal to 0.3 meters. This is R2. The value of R2 I'm taking is equal to 0.5 meters. Same data I'm taking. Okay. The value of net discharge is equal to 3 liters per second. Again, I'm having mostly what happens is you'll have Q by 2 and Q by 2 on either side. Okay. This is nozzle 1, this is nozzle 2. The cross-section area 1 is equal to cross-section area 2 is equal to 1.5 centimeter square. The cross sections are like this, and the rotation will be given to you. The rotation is again over here. One second. This time it is clockwise. This time the rotation is clockwise, please. The rotation is clockwise. And any other data was required? Yes, R1 and R2 mentioned over here. Density is again equal to 1000. Density is again equal to 1000 kg per meter cube. Again, the question is find omega if the net torque, or he can also say net frictional torque at hinge is 0. Net frictional torque at hinge is 0. Okay, net frictional torque over here is equal to 0, or net resisting torque is equal to 0. These kind of words he can use over here. You're supposed to find out the value of omega. Just by the virtue of fluid coming out, this is going into some kind of rotation. Okay. Now, how do you find this omega over here? How do you find the value of omega over here? To find the value of omega, you are going to start with a line diagram. I'm giving you 1 minute. Draw the line diagram. Look at this entire. Look at this entire diagram and draw the line diagram. If both the nozzles on same side, will it rotate? Yes, it will rotate if you are not having R1 equal to R2. If R1 becomes equal to R2, then rotation is not possible. Okay, next thing, how is it clockwise? It is clockwise because if you think of little logic, you will see that this lever arm is higher. That means the motion of U2 is going to create, or it is going to dominate over U1 over here. Okay, U1 is downward. Sorry, U1 is U1 is downward, U2 is downward. This U2 is going to create clockwise effect. U1 is going to create anti-clockwise effect. Who will dominate? Whose ever lever arm is higher, that will dominate. Since R2 is higher, his lever arm will dominate. Draw line diagram. I'm waiting for your line diagram first of all. If discharge is different, yes, then also it can rotate. I hope you have all drawn the line diagram. Sorry. If you have drawn the line diagram, now I'm going to draw the line diagram. The diagram is going to be something like this. Please observe. This, let us say, the lever we are having. This is the entire system assembly we are having. I'm taking some point over here, point O. This point, let us say, is point 1. This point, let us say, is point 2. First thing, I'm going to show absolute velocity with red line. Okay. V1 over here, V2 over here. I hope all of you are getting this thing. Next, u1 and u2. See, it is given to me in the question. Remember, omega's direction will be given to you in the question. Omega is given to you in the question. Now, because of this omega, what is going to happen? Because of this omega, you're going to have, one second, rotation is this way, right? u1 over here and over here, u2 in this direction, u2 in this direction. Okay. Next, after this thing, relative velocity. I'm showing relative velocity over here like this. Please don't raise hand. Achha, the value of u1 and u2, first of all, value of u1 and u2. u1 is equal to 0.3 omega, u2 value is equal to 0.5 omega. ठीक है. This is VR1, which is equal to, now look over here, both of them in the same direction. If both of them in the same direction, then what will happen? V1 vector minus U1 vector is V1 minus U1. That is equal to V1 minus 0.3 omega. Now over here, VR2 is equal to, both in opposite direction, that means V2 plus 0.5 omega. Now, why are we doing all these things? Our aim ultimately is to develop the equation of V1 and V2 in terms of VR1 and VR2. The value of V1 over here is equal to VR1 plus 0.3 omega, and V2 is equal to VR2 minus 0.5 omega. These are the velocities. After having, I hope you are able to get these velocities. I hope you are able to get these velocities. See, u1 and u2 कैसे decide करेंगे आप? How will you decide u1 u2? ये rotation ऐसे हो रहा है. If the rotation is clockwise, imagine this is moving in clockwise direction. So u1 ऊपर है. This is clockwise. This is moving down likewise. चलिए. After all these things, next first step is done with. Second step, you have to develop the value of VR1 and VR2. How do you do that? I told you already. Talk about discharge now. Q1 is equal to A1 into VR1, which implies VR1 is equal to. Similarly, Q2 is equal to A2 into VR2, implies VR2 is equal to. VR2 is equal to. Now, if you see over here, yes, direction of rotation is given in the question. Direction of relative velocity should be in the direction of absolute velocity. If V1 is upward, VR1 is upward. If V2 is downward, VR2 is downward. Likewise. 1 second, please. After having done this thing, you can get the value of VR and VR2. Previously, whatever area I have taken, same area I have taken again. Previously, whatever discharge I have taken, same discharge I have taken again. So the value of VR and VR2 are going to be equal to 10 meters per second. And likewise over here, you're going to have 10 meters per second. Okay, finished in here. Now the equation of torque. Look over here. This is where people do mistakes. The equation of torque. Torque is equal to T1 plus T2. It is given to be the net torque is equal to 0. Now look carefully. With respect to this point O, he is creating some clockwise direction. Look at VR1 and V1. They are creating what kind of direction? Clockwise. With respect to point O, he is creating which direction? Anti-clockwise direction. Please observe. Are both the directions same? No, both of them are not same. If both the direction senses are opposite, then I have to take one as positive, the other as negative. I'm supposed to take one as positive, the other as negative. Let us say I'm taking anti-clockwise positive. So clockwise is negative. Therefore, this has to be minus m dot 1 v1 r1, and this has to be plus m dot 2 v2 r2, m dot 2 v2. From here, it implies that m dot 1 v1 r1 has to be equal to m dot 2 v2 r2. Now I can cancel up m dot 1 and m dot 2. Actually, finish off and get me the value of omega. Please start. V1 is VR1 plus 0.3 omega. So 10 plus 0.3 omega into 0.3 has to be equal to 10 minus 0.5 omega into 0.5, which implies 3 plus 0.09 omega has to be equal to 5 minus 0.25 omega, which implies 0.34 omega is equal to 2, which implies omega is equal to 2 divided by 0.34, approximately 6 you should get. .88, approximately 6 is fine. This is equal to 5.88 radian per second. This kind of problem appeared in GATE examination for 2 marks. Okay. The problem was where both the nozzles were facing in the same direction. Okay, omega's direction. Some of you might be having this doubt regarding the direction of omega. Do not worry about that. Omega's direction is given in the question. The direction of omega is given in the question. Okay. Once the direction of omega is given, see, I cannot go into the details of mechanics. You should know if omega's direction is given, what is the direction of V1, sorry, U1. You should know that this particle is going to rotate in clockwise. इसका tangential velocity कहाँ है? ऊपर है. Likewise, this particle, if rotation is clockwise, this particle is moving down, this particle is moving up. That much also, if I keep explaining, then it is not possible for me to complete. Okay? So omega's direction will be given to you, and once omega direction is given, then relative velocity. Again, see, till here nothing is fluid mechanics. Till here nothing is fluid mechanics. The relative velocity, how to find out relative velocity? Absolute velocity minus the velocity of the nozzle. Yes, Ganesh, correct. I have taken u in the torque equation. If you see in the torque equation, this V1 is having u present. Actually, with this, we complete the concept of momentum equation. You can take the slides very quickly. This was the first slide we were having where we introduced the concept. Be quick in taking down the snapshots. This was the first slide for today's class where we introduced the concept. The second slide where we saw the first problem. I told you 3 steps are there. First step is the line diagram of velocities. Second step is for discharge. And this is the third slide for today, the equation of torque. One more problem. This was a gate problem. I don't remember the numbers actually. Whatever numbers were given in GATE examination, I don't remember. But I at least remember that in GATE examination, for 2 marks, a question was asked where both the nozzles were facing in the same direction. Okay. Finally, this is a solution. With this, we complete the equation of momentum equation. With respect to this particular center, you are having one velocity or one kind of motion. It is in one direction. With respect to this, you are having this in the other direction. Those two are in the opposite directions over here. You see, omega's direction will be given to you in the question. You don't have to worry about the direction of omega. Once omega's direction is given to you in the question, according to that, you decide u1 and u2's direction. In the case of inclined nozzle, very good. In the case of inclined nozzle, you are supposed to have the component of force in the vertical, because you see, if it is inclined, imagine if it is inclined like this. Let us say V2 is inclined like this. Then I'm not going to have this V2 creating the torque. The component of V2 coming over here will be creating the torque. Again, accordingly, I'll have to find out relative velocity. That kind of problem will become highly complex. It is not possible in GATE examination. That kind of problem I'll discuss if required in your IES conventional class. That time it might be important. Let us now move further. Till here, what we have studied was momentum equation application. Let me quickly summarize what we have studied till now. We have finished the concept of statics. Yes, it is equilibrium condition. Now let us stop this thing. If you have doubts, you can discuss with me later on. Let me move forward now. Okay. Chaliye. Come on, stop now. Chaliye. Till here, what we have discussed is the concept of momentum equation. Please understand, we have started with the concept of statics. Statics was a completely different subject. After statics, we went for kinematics plus dynamics. Kinematics plus dynamics. In kinematics, you have seen something known as continuity equation. In dynamics, you have seen Bernoulli equation and momentum equation. Bernoulli equation, momentum equation. The ranking of importance is also same. This is the most important. Continuity equation is the most important. Without this, you can never talk about flow. After continuity equation, Bernoulli equation is important. The least important for you will be momentum equation. From here onwards, very rarely you are going to come across any kind of problem which is influenced by momentum equation. Okay. You are going to see mostly continuity and Bernoulli. Actually, momentum equation is there, but the results due to momentum equation are generalized already. For example, you might be aware of a particular equation known as Darcy-Weisbach equation, which is head loss is equal to FLV square by 2GD, or 1 by 12.1 FLQ square by D power 5. This kind of equation is there. Okay. Now, whenever we write this equation, after writing this equation, we might use continuity, we might use Bernoulli, but we rarely use this momentum equation. But actually, strictly speaking, in deriving this equation of head loss, momentum equation was contributing over here. So what is going to happen? I'm telling you what will happen in the subject as we move forward. As we move forward from here onwards, you will keep on looking at continuity equation, Bernoulli equation. You won't look at momentum equation because the results by the virtue of momentum equation have already been established and they have been generalized. They have been generalized already. Fine. Now, let me tell you what our subject is going to deal with. These three equations we have defined: continuity, Bernoulli, and momentum. These three equations are the tools. We only have three equations in entire subject, three governing equations in entire subject: continuity, Bernoulli, momentum. That's it. Based on these three equations, we are going to have different types of problems. We are having three problems. First problem is known as internal flow problem. Second is known as external flow problem. Third is known as open channel flow problem. Our discussion is going to deal with the first two problems, which is internal flow and external flow. Okay, internal and external flow. So now my topic is going to be internal. So my chapter's name right now is internal flow. Internal flow. I'm telling you, please do not comment for some time. How much duration of course is left? The duration of course will be around, internal flow will take somewhere around 10 hours. External flow will take around 5 hours. That will be the course for civil. After that, for mechanical, I'll have to take two more topics, which is known as dimension analysis and hydraulic machinery. Again, another some 5-6 hours will be left. Okay, hopefully in that much time you can finish off. Now listen to this. Internal flow. Strictly speaking, internal flow in your literature is going to have three chapters. If you look into your literature, you might find internal flow is having three chapters. First chapter's name is laminar flow. First chapter's name is laminar flow. Second chapter's name is flow through pipes. Flow through pipes. And last chapter's name is turbulent flow. Turbulent flow. Okay. Don't worry, from here onwards, the subject will become relatively easy. The subject is difficult in this particular range. This particular range, subject is difficult. But after this range, subject becomes very easy and subject becomes more logical also, because you'll have less mathematics. The reason why you are having difficulty over here is more mechanics and mathematics. That is why you are feeling difficulty. You are having more mechanics and mathematics over here. That is why you are feeling difficult. Kinematics, completely calculus. In dynamics, complete thing is mechanics only. Okay, that is why you are probably feeling some difficulty. But over here, you are not going to have that much difficulty. The reason is, over here some standard formulas are present which are supposed to be derived, but we won't do the derivation. Derivation is not required for our subject right now. Okay, once we know the standard formulas, we just have to go along the standard formulas and get the results. So these three chapters are mentioned under internal flow in your literature. But what I'm going to do is, I'm going to break down these three into four actually. I'm going to have four. The first thing over here is basics of internal flow. This is the most important thing. Basics of internal flow. This is the most important thing. What I'm doing is, some portion of flow through pipes, listen carefully, some portion of flow through pipes I'm going to discuss before only. Before laminar flow, I'm going to discuss some portion of flow through pipes. That portion of flow through pipes I'm calling as what? Basics of internal flow. This is the most important part. Most important part. If you understand the basics of internal flow, rest of the things you will follow very, very easily. And this part is not going to have any questions. It is going to be just some theory. Basics of internal flow, we won't have much questions over here. Only some theory we are going to have, which will take less than 1 hour. Once you understand this, rest 9 hours for you will be very simple. Okay, this is the most important part. And your examination point of view, most important part will be this thing. From here you will get questions. Okay, mostly a 2-mark question is possible from here. From flow through pipes, a question can appear for 2 marks. So this is the idea of the subject right now we are having. Okay. Internal flow is what do you call, is important for any examination you are going to attend. Okay, now listen to this.
It is important for both civil and mechanical, very important for both civil and mechanical. And for civil, even more important, very, very important. For mechanical also very important, but for civil, extra important. Why extra important? Whenever civil people sit in some interviews which are based on water resource department and all those things, that time questions from flow through pipes are very frequent. Okay, if you are having these state level examinations where you are having water board department and all, over there when you want jobs, that time flow through pipes question guarantee they'll ask you in examination as well as in interviews. Chali, let us now move further. Believe me, the subject is going to be relatively simple from here onwards. I'm not going to do derivation. If I do derivation, it becomes interesting, but that much time is not there. It is not required also. And once we start doing derivation, you will understand how these three equations are actually influencing. Every derivation, remember this thing, every derivation is going to be a combination of these three equations. The subject becomes easy and difficult both at the same point. Since we are having only three equations, it is easy. And since we are having only three equations, it is difficult. Okay. It is just based on how well you understand these three equations. Don't worry, from your point of view, you don't have to worry much about this because we are not doing derivation. Straight away, results le rahe hum log and we are solving questions. Let us now start. The chapter now I'm going, please don't say anything now. You listen to my story. My story is very interesting now. And if you listen, you will understand. I guarantee you this. After years of teaching, I have attained this kind of flow, means this kind of chronology. Okay. If I teach initially, I straight away started with laminar flow, but it was difficult. Therefore, what I did after experience, I could divide this portion into some part and put over here. Now the subject becomes easy. You listen and you put some effort from your side also. If you think that only I am supposed to say and you're not going to put any effort, you will never understand. Believe me. You put some effort from your side. You try to understand. Okay. And if you're not understanding, be patient sometimes. It is possible that after the topic finishes, things will get clear to you. Okay, be patient and listen. You will understand, guarantee. Chaliye, let us start now. Let me be fast, please. Now, the topic I'm discussing right now is basics of internal flow. Basics of internal flow. Chaliye. Small topic, probably around 1 hour. Strictly speaking, it is not an individual chapter. It is actually a part of flow through pipes, which I'm starting over here itself. First thing, what do we mean by internal flow? How is an internal flow characterized? Please understand, whenever you are having a flow through a certain passage such that the gauge pressure is not zero, we call that kind of flow as internal flow. Imagine I'm having certain passage over here. I'm having certain passage over here. This is a pipe, for example. Let us say the passage I have chosen over here is a pipe. It is a pipe. Okay. Now in this pipe, I'm having some fluid flowing. There is some fluid flowing. If this fluid is going to have two primary characteristics, first primary characteristic is no free surface. No free surface. And second characteristic is the gauge pressure is not equal to zero. The gauge pressure is not equal to zero. Then we say this particular flow has now become for me internal flow. This has become internal flow. Two primary characteristics are required. Free surface should not be there and the gauge pressure should not be zero. Actually, both of them are interlinked. Imagine if you are having a free surface. Imagine a particular passage, let us say. Imagine a particular passage. In the, 1 second. 1 minute, please. Array, 1 minute, please. Imagine this particular case. Over here, you see you're having a free surface. If you have a free surface, if you have a free surface, eventually at this particular point, the gauge pressure is going to be equal to 0. In this particular case, you're going to call the flow as your open channel flow. You're going to call your flow as open channel flow, which is not a part of our curriculum right now. Civil people probably are already taught open channel flow. Mechanical, not a part of your curriculum at all. Okay. Now, remember, whenever you are having internal flow, the flow is going to be governed by pressure, or pressure is going to drive the flow. Pressure forces drive flow. Pressure forces are driving flow. Now over here, who is going to drive the flow? Gravity forces will drive the flow. Gravity forces drive flow. Gravity forces are going to drive the flow. This is regarding the basic difference between internal flow and open channel flow. You have to understand this thing. I'll give you an example now. Imagine right now I'm having a bottle of water. I want to drink water. I want to drink water. So what I can do is I can create a gradient, an elevation gradient for this bottle. Let us say something like this. When I create an elevation gradient, then I'm having a free surface and I'm creating some kind of tilt so that the water is coming down. I'm allowing the gravity forces to create the flow. That particular flow of water was open channel flow. One more thing which we don't generally use is, let us say I put in a straw. I put in a straw and I siphon off the liquid. I pull off the liquid by creating some vacuum pressure inside my mouth. By creating some vacuum pressure inside my mouth, I'm having a higher pressure inside the bottle, vacuum pressure inside the mouth. The difference in pressure is creating a flow inside the straw. That straw is going to have completely filled fluid. जैसे कि यहाँ पे है. Imagine the cross section of straw. It is going to have completely filled fluid, no free surface, no zero gauge pressure on the interface. Interface is not there, so no zero gauge pressure. The flow over there is driven by pressure forces. So the flow inside the straw would have been what kind of flow? Internal flow. I hope you are following this thing. These are the two flows we are having. We are going to be interested only in internal flow. So first thing is done with. We have understood what internal flow is. Second thing over here, इसको आप point 1 ले लीजिए. Second thing over here, whenever you are having internal flow, you are supposed to classify the flow. And when you are classifying the flow, a particular number becomes very important. Okay, all of you might be knowing about that number already. That number is called as Reynolds number. That number plays an important role. Now the question is, why is this number important for us? You see, throughout this chapter or throughout this internal flow, we are going to discuss about real fluids. Real fluids are flowing over here. If real fluids are flowing, then viscous forces are going to contribute in the flow. If viscous forces are contributing, we are looking at the relative effect of viscous forces on the flow. And that relative effect of viscous forces is given by Reynolds number. Okay. If you're not following, be patient. Everything will fall into place if you are patient. The concept now is Reynolds number. Reynolds number. You see, every internal flow is influenced by viscous effects. Viscous effects. It is going to be influenced by viscous effects. Therefore, the dimensional ratio of which two forces? Now this is important. inertia and viscous forces. Inertia and viscous forces is helpful in classifying or differentiating, distinguishing, कुछ भी बोल लीजिए आप, classifying flow. Now the dimensional ratio of these two forces is called as which number? It is called as Reynolds number. Dimensional ratio of these two numbers is basically your Reynolds number. That is Reynolds number. Now what is the formula of Reynolds number? Let me mention over here the formula of Reynolds number. Reynolds number is represented by RE. Okay. Dimensional ratio of this dimensional ratio of inertia and viscous forces is given by rho into V into L divided by mu. This is the formula we are having. Rho density, V velocity, mu viscosity. Everyone knows this thing. What is L? What is L? L over here is the characteristic length of flow. Characteristic length of flow. L over here is known as characteristic length of flow. In the case of pipe, the characteristic length is going to be the diameter of pipe. So I can write over here, in pipe flow, L has to be diameter. Therefore, the Reynolds number in pipe flow will become what? RE in pipe flow will become what? It is going to become rho V into D divided by mu. It is going to be rho VD by mu. As a matter of fact, there is a standard classification using Reynolds number in a pipe flow. That classification stands something like this. Most of you might be aware of this. Less than or equal to 2000, you have a particular flow. Ranging between 2000 to 4000, you are having a particular flow. And beyond 4000, you are having a particular flow. Now, these names are quite famous. And as a matter of fact, these names are going to be individual chapters also. We'll discuss about them in detail later on. Right now, my aim is just to mention the names. The first one is known as laminar flow. Laminar flow. The last one is known as turbulent flow. Please understand, strictly speaking, there are only two flows, laminar flow and turbulent flow. So, बीच में क्या है? What is there in middle over here? That middle region is the transition from laminar to turbulent. देखा जाए तो you're only having two things. That middle thing is a bridge between them. Okay, that is known as transitional flow. Transitional flow. Transitional flow. It is basically a region where a region where you are having conversion from laminar to turbulent. Conversion to laminar to from laminar to turbulent. That is known as your transitional flow. ठीक है. Now, sometimes what happens is in your examinations, you can have passages which are not pipes. For example, over here, the passage is a pipe. It is possible you can have a duct also. There is something known as a duct. There is something known as a duct. Duct basically is a passage having non-circular cross section. Non-circular cross section. Example. If you have seen in big malls, okay, near the cellar or the basement, you'll be having AC ducts. Now these AC ducts are not having circular cross section. Mostly you'll be having rectangular cross section. Mostly ye hai. Apart from rectangular also you can have different cross section. Most of the times you're going to have rectangular cross section. So imagine you are having some kind of a passage like this. This is a duct over here. This is a duct. Let us say the fluid flowing over here is something like this. You are having some fluid flowing over here. Fluid flowing over here. One more important thing regarding duct is Okay, mostly gases are used as working fluid in duct. Working fluid in duct. So whenever you're having duct flow, be assured that question will have a gas inside. Okay, AC duct also is going to have gas on it. Okay, so this is called as a duct. Over here, the characteristic length of flow. The characteristic length of flow. The characteristic length of flow, L, is equal to how much? What is the value of this L? L over here is given by hydraulic diameter, dH. It is known as what? Hydraulic diameter. Okay, these things will be important in your heat transfer also. Okay, you might be having the concept of ducting and hydraulic diameter in heat transfer. Similarly, for civil, open channel flow will have the concept of hydraulic diameter. What is this hydraulic diameter formula? It is equal to 4 times area upon perimeter. This A over here is known as wetted area. Wetted area. And P over here is known as perimeter. Perimeter. For example, let us say in this particular case, this is equal to L and this is equal to H. Okay, let us not take L because per character, one second. Let us not take L, let us take B over here. Okay, because L already we have used. So L over here, the characteristic length over here is hydraulic diameter, which is over here equal to how much? 4 times area upon perimeter. So the value of D hydraulic is going to be equal to how much? It is going to be equal to 4 times. What is the area over here? Area is B times H. Area is B times H. Perimeter over here is equal to how much? Perimeter of a rectangle, 2 times B into H. Therefore, the value of D hydraulic over here will be equal to 2 times BH upon B plus H. This should be the value. And using this, you'll use this as your characteristic length, and you will see your Reynolds number is equal to rho V into D hydraulic divided by mu. This is what we are going to have in the case of ducts. In the case of ducts. If you have circular cross section, it is not called as a duct, it is called as a pipe. Okay. For circular cross section, we use the word pipe. For non-circular cross section, we use the word duct. Okay. So this is regarding the second point. First point I have defined to you, I have mentioned to you what is an internal flow. What are the characteristics of internal flow? Basic characteristics. Okay. Many more characteristics are there which we'll discuss as we go forward. Second thing I told you that there's a very important number which is going to classify the flow, and that number is known as Reynolds number. That Reynolds number is the dimensional ratio of inertia to viscous force given something like this. Okay. And if you are not having a pipe, and that is going to happen very rarely, extremely rarely, you're going to have a duct coming in. As a matter of fact, even though the concept of duct should be there, it has not been asked in your examination till now. Okay. This is regarding the concept of duct. Remember, working fluid inside a duct is mostly going to be a gas. Inside a pipe, it is mostly going to be a liquid. Moving further, now comes the third thing. Third thing over here is going to be lengthy, and this is going to the last thing. This is standard equations which are being followed or which are being obeyed in every internal flow through pipe, whether it is laminar, transition, or turbulent. Okay, any of these flow are going to follow some standard equations. Let me tell you. You see, they are having some differences, of course. These three flows are having some differences. Okay, so somewhere their equations are going to be different, but some governing equations are going to be still the same. Those same equations or those identical equations for every flow we are going to discuss now. So this particular point over here is equations common for every internal flow through pipe. Internal flow through pipe. Every internal flow through pipe is going to have some common equations. Whether it is laminar or transition or turbulent, they are supposed to follow these equations. Okay. Apart from these equations, the other equations will be different. For example, the equation of velocity in laminar flow through pipe and turbulent flow through pipe, both of them are different. But the equation of shear stress in laminar flow through pipe and turbulent flow through pipe, both of them will be same. That equation, which is common, that we are going to discuss. For example, the equation of shear stress, the equation of pressure drop, the equation of head loss. All these are some common equations. Okay. Laminar flow and turbulent flow, both of them will have same formula. That is what we are going to discuss over here. But these things are having some condition. Okay. Let me write that thing down. The following equations are followed by every internal flow as long as the flow is steady, as long as the flow is steady. Steady means what over here? The discharge in the pipe should be constant. Okay, the discharge in the pipe should be constant, and the flow is fully developed. The flow is fully developed. There is a concept known as development of flow that I will discuss later on. Right now, just understand that the flow is always fully developed for you. Okay, this concept of fully developed flow should be understood after boundary layer theory, much later topic. Right now, just accept there is something called as fully developed flow. So we are going to have a set of equations which are followed by laminar, transition, turbulent. Everyone is going to follow the same equation, but the condition, two conditions are there. Pehla condition kya hai? Flow should be steady. Second condition is flow is fully developed. Steady flow you have understood. Steady flow basically means discharge over here is going to remain constant. What is fully developed? We'll see sometime later on. Okay. Now we are going to see some equations over here. Let us see. First equation, A bit. Under third point, I'm having some equations. First equation over here is differential equation governing the flow. Differential equation governing the flow. What is the equation governing our flow? We are going to see over here. Very lengthy derivation is there, not required for you. Okay. Imagine you are having a pipe. Let me draw a diagram first of all. I'm having a pipe over here. Let us say this is a pipe I'm having. One second. Suppose this is the centroidal axis of the pipe. Let us say this is a pipe we are having. This is centroidal axis. Okay. Now listen carefully. Any pipe is going to be defined by only two axes. Only two axes are required to define a pipe. One axis is the central axis, which is represented by X. The other over here is the radial axis, which is represented by small r. It is represented by small r. So X is axis along flow, axis along flow, and R over here is radial axis. These two axes are important. Radial axis. These two axes over here are important. Okay. Now, what is the governing equation? The governing equation is represented by, I'm writing over here, R into minus dP upon dx has to be equal to d by dr of r times tau. This is the equation we are having. The equation is r into minus dP by dx is equal to d by dr of r times tau. Okay. Now what is this dP by dx over here? dP upon dx is basically the rate of change in pressure along flow. Tau, of course, is your shear stress. Tau is your shear stress. Tau is shear stress. Please understand this thing, that as you are moving along the flow, okay, as you are moving along the flow, what is going to happen to the total energy? Ask yourself this thing. Okay, I told you that when we are starting this chapter, I told you every flow over here is viscous, every flow over here is real. That means you are supposed to have losses. You cannot escape losses now. So as you are moving forward along the flow, you will have losses. Losses will be developed. If losses are developed, P plus K plus U is supposed to sacrifice itself. Now, who will sacrifice itself? Who will sacrifice itself? You see, kinetic energy will never sacrifice. Why will kinetic energy not sacrifice? Kinetic energy will say, as I move from here to here, the cross-section area here and here, both of them are same. If cross-section area, both of them are same, then according to continuity, because I have to satisfy continuity first. According to continuity equation, A1 EV1 equal to A2 V2, my velocity will be same. He'll say, okay, he is not sacrificing. I have a horizontal pipe, so he's also not sacrificing. Potential is also not sacrificing. Then who will sacrifice? Remember this thing. The burden of loss is always taken by whom over here? Pressure. That I'm going to discuss again later on. Sometime later in the concept of losses, we'll be seeing the burden of loss will always be taken by whom? Pressure. That means as I keep on moving forward, my loss is supposed to keep on increasing. And for my loss to keep on increasing, my pressure should keep on decreasing. I hope you are following all these things. Again, whenever I move forward in a flow, loss should increase. Total energy should decrease. In total energy, the only one taking the burden of decreasing is pressure. So as I move forward with respect to x-axis, my pressure should decrease. That is why I'm writing dP by dx. Since pressure is decreasing in the equation, I'm not even having plus dP by dx. I'm having over here, please observe, I'm having over here what? Minus dP by dx. I'm having over here minus dP by dx. I cannot stress any more over this minus. I hope you are following here. Okay. Please don't raise hand at this stage. You please listen. Kinetic energy will not sacrifice because of continuity equation. Potential, because you are having a horizontal flow. Potential cannot sacrifice something you are giving. Potential is something which you are deciding. It won't sacrifice. So this is the governing equation. You have to memorize this thing. You have to memorize this. Derivation is there, not required. My second A-bit is differential equation. my B bit is going to be this particular part, that is minus dP by dx we are going to discuss. It is called as pressure gradient. This is called as what? Pressure gradient. This is called as pressure gradient. So B bit now I am discussing, it is known as pressure gradient. Please follow these things, because once you understand this, then remaining topics will be very, very easy. Even if no one teaches you, just by looking at the formulas, you will come to know what exactly is happening. That much easy the next topic is going to be if you are understanding this. Pressure gradient over here is represented by dP upon dx. Understand the physical meaning of gradient. Gradient basically means the rate at which something is changing. Okay. So right now pressure is changing with respect to the length along the flow. That is why dP by dx I'm having. Over here you have to understand some points. First point you have to understand is pressure. Now answer it to yourself. Don't type, answer it to yourself. Is it increasing or decreasing along the flow? अभी आप देखें, loss बढ़ रहा है, loss is increasing along the flow. So what will happen to pressure? Decreasing. Sacrifice kar, it is sacrificing. So pressure decreases. Very important word, decreases. How is it decreasing? It is, remember this thing, since the flow is steady, the decrease in pressure is supposed to be linear. Pressure, पहली चीज decrease, दूसरी चीज कैसे decrease? Linearly. Pressure decreases linearly along flow. Now this implies that the value of pressure should be proportional to, देखिए, whenever we say decrease, we are supposed to write minus x. Furthermore, linearly means power over here should be 1. So whatever I have written over here statement, I am converting that statement to a mathematical equation. Okay, decrease के लिए minus, linearly के लिए power 1. If power is decreasing linearly, if I'm having this particular situation, this further implies the value of dP upon dx will become a negative quantity. It becomes a negative quantity. And furthermore, it should become a constant. Remember, whenever you are having linear variation, slope will be constant. That is what I'm showing over here. Slope is constant. But what kind of slope? Because pressure is proportional to negative x, therefore the slope is negative. This further implies, very, very important thing I'm writing over here, very important thing. As long as the flow is steady, negative of dP upon dx is going to be a positive constant. Please put some effort from your side and understand this thing. Pressure decreases linearly. So ye ho gaya. If you differentiate, it will be negative constant. Therefore, negative dP by dx is a positive constant. This negative dP by dx is actually, you can say, amount of pressure drop per unit length. इसको क्या बोल सकते हैं आप? What will you call this thing? You can call this thing as pressure drop per unit length. It is representing pressure drop. क्यों drop क्यों बोल रहा हूं मैं? क्योंकि you are having negative dP. Basically pressure is decreasing. इसलिए pressure drop. Per dx means per unit length. Pressure drop per unit length. Now listen to this. Every step is important. I cannot emphasize more. You have to please understand this thing. Since it is a constant, देखिए, if you are having a line, any point is going to have same slope. That is what? The slope is remaining constant. Since it is a constant, what I can do is, wherever I see minus dP by dx, I can replace it by delta P upon L. This equation, if you understand mathematics, you can appreciate this equation. Okay, this equation is saying if the slope is constant, a small portion is going to have same gradient as a big portion is going to have. वो कब हो सकता? सिर्फ constant slope के लिए हो सकता. Delta P over here is representing pressure drop. Delta P is representing pressure drop. And L is representing. Okay, please, delta P does not mean pressure change. Delta P over here means pressure drop. Pressure drop मतलब क्या है? Initial pressure minus final pressure. Initial pressure minus final pressure. That is pressure drop. Generally क्या होता? Delta, whenever we see delta, we think it is change. Change means final minus initial. But over here, you see, I am replacing minus dp. Matlab, I am supposed to talk about initial minus final. That is why it is called as pressure drop. And L over here is length of pipe. Length of pipe. L over here is length of pipe. Now, in this particular slide, this is very important slide. Okay. Strictly speaking, you don't have to memorize anything. अगर आपको समझ में आ गया, तो it is sufficient. But still, if you're finding difficulty, memorize this particular line. Memorize this particular line and memorize this particular thing. Memorize this thing. Memorize this thing. When to use all these equations, I'll tell you, don't worry. When to use all these equations, I'm going to tell you. Okay. So for those who could not listen because probably the sound someone is complaining was low, I'm again telling you very quickly, everything, whatever I've told, I have written also over here. So if you have missed something, you have not missed anything actually. The concept is pressure should decrease. How should it decrease? Linearly. Uska effect kya ho raha? What is the effect of that thing? The effect is minus dp by dx is going to become a positive constant. ठीक है. If minus dp by dx is positive constant, for a small part of pipe, minus dp by dx will be equal to, for a big part of pipe, delta p by L. Delta p over here is pressure drop. ठीक है. This is regarding the second point. Now comes the third point. देखिए, this thing I hope is clear to all of you. That is minus dp by dx is clear to all of you. Now I'm coming to this particular point. This is probably the most important point in the entire chapter, tau, which is called as your shear stress. Tau is called as shear stress. Yes, delta P by L is a constant. For a particular pipe, delta P by L has to be a constant. Okay, now comes the third point over here. Third point, shear stress. Expect question from here. Expect a question from here. Very, very important. Very, very important and very, very simple equation. Very simple equation. We are going to see shear stress profile also over here. Okay. Now, the equation of shear stress. I'm going to start with the governing equation. The governing equation told me some time back that R into minus dP upon dx has to be equal to d by dr of R times tau. This equation you have to accept. A governing equation hai. One more thing you have to accept now. This is a constant value. Delta P by L or minus dP by dx is a constant value. This is a constant value. That to a positive constant value. Minus dikh raha aapko. You are seeing minus over here, but it is not a negative quantity. It's a positive constant. A net value is positive value only over here. Now what I'm going to do, I am going to imply from here that d of R times tau has to be equal to minus dP upon dx multiplied to R times dr. Okay, accepted. All I did is I took this dr over here. Okay, ठीक है. अब next करेंगे हम integrate. Next we are integrating. And I'm putting this outside. All of you know constant है इसलिए outside है वो. At R equal to 0, that's the center line of the pipe. center line of the pipe, R into tau is equal to 0. At any random radius, R into tau is R into tau. If I integrate over here this thing, I'm going to get R into tau is equal to minus dp upon dx multiplied to R square by 2. Cancel one R and one R. You're going to develop the equation of tau now. You're going to have the equation of tau. Let me write in red. The equation of tau you are going to get. Very simple equation. And that is minus dp by dx multiplied to R by 2. Or tell me, can I write this delta p by L multiplied to R by 2? Yes, I can write. Okay, minus dp by dx multiplied to R by 2 or delta p by L multiplied to R by 2. This is the value of shear stress in the case of every internal flow. भले laminar हो या turbulent हो या transition हो, be it laminar, transition or turbulent, any which case, the formula for tau will remain the same. Very simple formula, minus dp by dx multiplied to R by 2. Now please observe over here, minus dp by dx constant है, 2 is a constant over here. If both these things are constant, from here I can imply that my shear stress is supposed to be proportional to R power 1. That means shear stress increases linearly with respect to R. Shear stress is going to increase linearly with respect to R. This is where we are supposed to draw a particular diagram known as shear stress profile. Very famous and very important diagram. Shear stress profile. Let us see what this shear stress profile is. Imagine this is a pipe you are having. This is a pipe you are having. This is a pipe, let us say. Suppose I have a center line. I have a center line. One moment, please. This, let us say, the center line of the pipe I'm having. If I look at the shear stress, the profile of shear stress is supposed to be linearly increasing. Therefore, something like this. Shear symmetry should be there. If my diagram is not showing symmetry, you imagine symmetry then. This is the profile of shear stress you are going to have. This is the profile of shear stress. Now, you see, if I'm taking any random radius, then that particular shear stress is tau represented by this thing. If I take the complete radius capital R, then that shear stress is the maximum shear stress from here till here. That is the maximum shear stress. This maximum shear stress over here is known as wall or boundary shear stress. Wall or boundary shear stress. Very significant shear stress. You'll see in the next slide why it is significant. अब इसकी value कितनी रहती? What is the value of this wall or boundary shear stress? The value of wall or boundary shear stress tau naught has to be equal to how much? Minus dp by dx multiplied to R by 2. But which R will you take? You will take now capital R by 2. This is the value of wall or boundary shear stress. So this slide is very important. Over here, what do you have to remember? you have to memorize this particular formula. Memorize this particular formula. This is regarding the concept of shear stress in the case of every internal flow through pipe. Okay. It is a case of every internal flow through pipe. One moment, please. One second. Okay. Now coming to the next thing, I told you the shear stress is important. Wall shear stress is important for us. Wall shear stress is important for us. Let us look at the significance of wall shear stress. That significant of wall shear stress is my point D over here. That significant of wall shear stress is my point D. This point D over here is going to speak about friction coefficient and friction velocity. Friction coefficient and friction factor, not velocity, friction factor. Friction factor. Friction coefficient and friction factor. Okay. Let me write a statement over here. The statement goes something like this. The statement says the ratio of wall shear stress, that is tau naught. By wall shear stress we mean tau naught, and the dynamic pressure, by dynamic pressure we mean what? Rho v square by 2. याद है आपको, half rho v square was dynamic pressure, is known as coefficient of friction or friction coefficient, anything you can say, is known as coefficient of friction. It is known as coefficient of friction, and this coefficient of friction is represented by F with a prime over here. It is represented by F prime. Okay, so the value of this F prime, therefore has to be equal to tau naught upon half rho v square. The value of F prime has to be equal to tau naught. This slide is not that much important for your examination, but it is good if you know this thing. The value of F prime is known as coefficient of friction. In the case of internal flow, this coefficient of friction is known as Fanning's coefficient friction. In internal flow through pipe, this coefficient of friction is having a special name. That name is only for internal flow through pipe. नाम क्या है इसका? It is known as Fanning's coefficient of friction. Fanning's coefficient of friction. It is known as Fanning's coefficient of friction. This is in the case of internal flow through pipes. Next statement over here. Next statement is 4 times coefficient of friction is known as, very important thing, this is important now, is known as Darcy friction factor. This is known as Darcy friction factor. It is known as Darcy friction factor. So what is this Darcy friction factor? 4 times F prime is equal to F, which is equal to 4 times tau naught divided by half rho v square. This is known as your Darcy friction factor. Darcy friction factor. Now, let me tell you, at this point, listen carefully. I believe especially people from Maharashtra, in their curriculum, when they study engineering, that time they do not write F prime. They just write F for Fanning's coefficient and Darcy friction factor, this is 4F. So I'm mentioning over here, in especially Maharashtra, I believe, F represents Fanning's coefficient of friction and 4F is representing Darcy friction factor. Probably this happens in some of the universities. Okay, this is the convention followed. Okay, that is why when they say the formula for head loss by Darcy-Weisbach equation, they say 4FLV square by 2GD. Okay, some books write like this, but I am going to follow this convention. Okay, you can follow your convention if you are comfortable. I follow this convention. This is a standard convention followed by many books. F prime is used for Fanning's coefficient, and 4F prime I'm going to represent as F, and that is for Darcy friction factor. So this is also true for some books. It is fine. Okay. So my convention is F stands for Darcy friction factor. Probably your convention is F is Fanning's and 4F is Darcy. Check. You can take a snapshot of this slide if you want. Moving further to the last thing. Not last thing, let us say two more things I'll take. E bit first of all. E bit over here. E bit. There is something known as shear velocity or friction velocity. Shear velocity or friction velocity. Shear velocity or friction velocity. It is represented by V star. Significance of this thing we'll see in turbulent flow. Much later you'll find the significance of this thing. Let us first of all define this thing. It is an imaginary velocity which represents the wall shear stress in the units of velocity, in the units or dimensions of velocity. Okay, first of all, it is imaginary. Shear velocity or friction velocity is an imaginary thing. It is not a real velocity. It is actually the measure of wall shear stress in the dimensions of velocity. What is the formula for the shear velocity? The formula for V star shear velocity is equal to root over of tau naught by rho. Root over of tau naught by rho. Now you see over here, it is directly proportional to root tau naught. It is talking about wall shear stress. It is converting wall shear stress into velocity. Its importance will come much later. That time we'll discuss it in turbulent flow. It also has one more formula. It is also equal to V root over of F by 8. V root over of F by 8. Okay, my convention, I told you previously also, again I'm telling you, F over here is Darcy friction factor. Darcy friction factor. Those who have a habit of writing Darcy friction factor as 4F, whenever I write F, you write 4F. Whenever I write F, you write 4F. Okay. For me, F is Darcy friction factor. Okay. This is known as your shear velocity or friction velocity. You have to memorize this particular formula. Last thing now. Last thing with this internal basics of internal flow finishes. Last point over here. This point is known as Darcy-Weisbach equation, very famous equation. Darcy-Weisbach equation, very, very famous equation. Now, what is this equation? Major head loss in every steady internal flow through pipes is given by this particular equation. What is that equation saying? This equation is saying head loss, major head loss. You are going to see later on, there are two types of head losses. One is called as major, the other is called as minor. Okay, बाद में पढ़ेंगे उसको हम डिटेल में. Right now, let us just accept there is something called as major. This major head loss is given by FLV square by 2GD. Again, those who have a habit of writing Darcy friction factor as 4F, you will write 4FLV square by 2GD. I will write this thing only. It is also equal to 1 by 12.1 FLQ square by D power 5. This is the equation you have. This is the equation known as Darcy-Weisbach equation. This equation is known as Darcy-Weisbach equation. Okay. One more thing I forgot to mention over here, that in this particular slide, in the pressure gradient slide, one more thing I have to mention. I some time back mentioned that loss is by the virtue of pressure only. So therefore, the value of head loss, let us say H. This again is major head loss only. The value of head loss H has to be equal to, you see, loss is by the virtue of drop in pressure. So it is going to be equal to drop in pressure divided by gamma. It is going to be drop in pressure by gamma. So whatever is the drop in pressure, that is creating head loss. So drop in pressure by gamma will give you head loss, because we want head. So we have to divide by gamma over here. This thing I missed to mention. I got the idea from mentioning head loss. I felt that I missed this thing, so I came back over here. So these are the things you are supposed to remember. Okay. It won't take a lot of time to memorize all these things. Okay. Within half an hour, you can revise and memorize everything till here. Okay. What is the significance of see later on? Yes. Is it major? Yes. This head loss is major. This head loss again is a major head loss only we are talking about. It can represent minor head losses if the delta P is the delta P in minor losses. Whatever kind of delta P you are having, that type of head loss. Generally, we are talking in pressure gradient regarding major head loss delta P. So therefore, it is major head loss only over here. Here. This is regarding the concept. Now, when we have discussed these 6 things, if you see 6 things, first was governing equation, उसके बाद pressure gradient, उसके बाद shear stress, उसके बाद friction factor and friction coefficient, shear velocity, lastly Darcy-Weisbach equation. 6 things we have seen till now. These 6 things, whatever I have mentioned when a pipe is in horizontal orientation. Look over here. A note now I'm writing. Note. The above formulas are valid for flow through horizontal pipe. Now the question can appear, what about if the pipe is inclined? Never mind, we have a solution for that. if the pipe is inclined, pipe is non-horizontal. By non-horizontal, it can be vertical or inclined. It can be vertical or inclined. If the pipe is non-horizontal, then what to do? See, it is not difficult. If the pipe is non-horizontal, imagine the pipe is something like this. Imagine this is a pipe you are having. This is a pipe you are having. First thing you are going to do is replace every pressure term by piezometric pressure term. Piezometric pressure. So wherever you are having pressure, the term will now become piezometric pressure. So basically, wherever you saw P, you are going to now say P is not there, P star is there, because datum is differing. Along with pressure, you have to bring in datum's effect also. So along with static pressure, datum's pressure also, P plus rho gz will come. That is basically P star. Second thing, generally people have this doubt. Okay, sir, I'll do this thing, they'll say. Then they have a doubt. What about the x-axis? Because we are having dp star by dx. Now pressure gradient is going to become, one second, pressure gradient is going to become dp star by dx. Gradient will become dp star by dx. Now the question is, what is x? Is it x-axis? No, it is not x-axis. Please remember, x was defined as an axis, central axis along the flow. So x is this axis for me. Okay, x will still remain the axis. X is the centroidal axis along the flow. Centroidal axis along flow. Please understand this thing. X will be this axis, not the horizontal. X is not horizontal in this case for us. X is basically the axis along the flow. Basically, if you are having a vertical pipe, X is in y-axis then. Okay, it might look very absurd, but X is in y-axis in this particular case. Okay. Let us take an example. If I ask you in this particular pipe, what is the value of shear stress equal to? What will you answer? Look at the formula for shear stress. Shear stress formula dekhiye. You are having the formula for shear stress. Can I straight away write this formula? Can I straight away write dp by dx multiplied to minus dp by dx multiplied to r by 2? Can I write over here? Minus dp upon dx multiplied to r by 2? The answer is no, it is wrong. How to make this answer correct? How to make this answer correct? To make this correct, you write minus dp star by dx. Now this is correct. Are you following this thing? Again, x over here is not with respect to horizontal, it is still with respect to along the particular. Chali, are you following all these things? Very good question, Shankar. Bernoulli equation is valid for invisible fluid. Then what about this particular cases? In this cases, Bernoulli equation is valid. Only thing is, you are supposed to write head loss. If you remember, we have defined Bernoulli equation for real flow. We have defined Bernoulli equation for real flow. And in real flow, you are going to have head loss involved. Okay, you're just going to include head loss over here. Please try to follow these particular points. If you follow these points, then next class will be very easy for you. Okay. Slides will be, I'll give you all the slides. Don't worry. The PDF they'll be giving you. Don't worry about the slides. No, class is not over. I still have time. I want to use everything. Chali. Now, do one thing. I don't have literature, but I hope you are having literature. open open the open the page in which turbulent flow chapters questions are there. The page for turbulent flow chapters question. Turbulent flow questions are there. I think question number 5 is having that kind of question, that you're having 100-meter long pipe, 100-meter long pipe, in which head loss is equal to 10 meters. Head loss is equal to 10 meters. Diameter is equal to some 100 mm. Check, is that kind of question there? What is the value of wall shear stress equal to? Check, is that question present? Turbulent flow chapter खोलिए आप. Question number बोलिए आप मेरे को. Question number बोलिए. Tell me the question number, please. Okay. In some books, it is page 97, question number 5. Chaliए, start that question. You can do that question. It is around page 97. I told you different books will have different page numbers, but the question number will remain same. This is question number 5. Chaliए. Yeah, 0.1 kilometer is 100 meters. Okay, page 91 in some books. Page 91 in some books. Turbulent flow chapter questions. Okay. The question goes something like this. You are having water flowing. The moment he says water, you know the density also. Density is equal to 1000 kg per meter cube. So he says water is flowing, 100-meter long pipe. The head loss is equal to 10 meters. The diameter is equal to 100 mm. What is the value of your wall shear stress? He's asking. What is the value of wall shear stress? He's asking. How will you find out the value of wall shear stress over here? Chali. We know some formulas. I'm going to show you the formula for wall shear stress. You take down the formula first of all. You take down the entire thing. ये पूरा चीज ले लीजिए. लिखिए this wall shear stress value. Minus dp by dx multiplied to r by 2 delta p by l multiplied to r by 2. Write this thing. Okay, I hope you have written this thing. So basically the value of wall shear stress has to be equal to minus dp upon dx multiplied to capital R by 2 आएगा. That is also equal to delta p by L multiplied to capital R by 2. This is a 1 mark question in examination. Okay. Now you observe over here, I have the value of R. Diameter is given, so R is given to me. I have the value of length. Length is equal to over here 100 meters. But what I don't have the value of delta P. I don't have the value of delta P. Somehow I have to adjust the value of delta P. How can I adjust the value of delta P? Sometime back we said that whatever is a pressure drop is contributing towards head loss. That means we have one more equation which says head loss is equal to how much? Delta P by gamma, which implies delta P is equal to how much? Gamma times head loss, or equal to rho into G times head loss. Rho into G times head loss. This implies the value of tau naught has to be now equal to, I'm using this particular part. In place of delta P, I'm writing density into G multiplied to head loss divided by L multiplied to R by 2. This is the value I'm having over here. So let me do one thing. Let me write in place of R by 2 D by 4. D by 4. So this value is going to be equal to how much? 1000 into 9.81 into head loss is 10. Diameter is equal to, in meters, 0.1 meter divided by 4 times length is equal to how much? 100 meters. You can calculate this value. This value, if you check, will come out to be equal to how much? $24.52. So this implies the value of tau naught is equal to 24.52 Pascal. The value of tau naught is 24.52 Pascal. Okay. Now in the entire question, did he mention to you anywhere that it is laminar flow or turbulent flow? In the entire question, did he mention anywhere whether it is laminar flow or turbulent flow? Nothing. He did not mention anything like that. If he is not mentioning, still we are able to solve, because whatever type of flow, be it laminar or turbulent or transition, okay. Achha, he has mentioned. Never mind. If he has mentioned or he does not mention, still whatever type of flow it is, okay, let us say it was not, it is mentioned though, but let us say we do not know what type of flow it is. If it is not even known which type of flow it is, whether it is laminar or turbulent, still we can use these formulas, because these formulas are universal for whether it is laminar or transition or turbulent. Any which case, you are going to have the same formulas. You're supposed to have same formulas. Now, one more thing I want you to observe over here is someone is asking me a very good question, that why is viscosity not creating the concept of shear stress? You see, shear stress over here is equal to minus dp upon dx multiplied to r by 2. This is what I wrote. Why am I not writing viscosity anywhere? Please understand, viscosity has affected already delta p, and that delta p is affecting over here. Viscosity already has created its effect. On whom? On drop in pressure. You see, if you want to visualize, you can visualize like this. Imagine a particular pipe we're having. Okay. Those who want to leave can leave. Today's class is almost over. This is just something to visualize, I'm telling you. Let us see. Otherwise, let me put it this way. 1 second. Let me put it this way. 1 minute, please. Let me make it even more clear. Understand like this. Imagine, all of you know that a real flow takes place from higher total head to lower total head, is it not? Let us say there are two reservoirs I'm having. There are two reservoirs I'm having. Okay. And I'm connecting these two reservoirs using a particular pipe. I'm connecting these two reservoirs using a particular pipe. Let us say over here I'm having fluid at this particular level. Over here I'm having fluid at this particular level. I'm connecting these two reservoirs using some pipe over here. I'm connecting these two reservoirs using this pipe over here. So when the liquid is flowing, from here to here, let us say the liquid is flowing from here to here. You're having the liquid flowing. When the liquid flows from here to here, what is going to happen? At the wall, there is going to be some shear stress developed. Let us say some shear stress is developed. This shear stress is by the virtue of viscosity. Okay. This shear stress is by the virtue of viscosity. In some cases, surface roughness and all those things will create shear stress. Some shear stress is developed. Now, because of this shear stress, you're going to have losses. Because of shear stress, you're going to have losses. And because of loss, someone has to sacrifice. So it's sacrificing. Who is doing that sacrifice? Delta P. Now, ultimately, delta P is also related to shear stress. This is a cyclic kind of nature. You're having. The delta P is also affected by shear stress. So whatever is a drop in pressure is having an influence of viscosity. It is having an influence on shear stress. All of them are connected to each other. So as the fluid particle tries to move forward, there will be some shear stresses in the backward direction. these are itself going to prepare your head losses also. If the pipe is inclined, then instead of delta P, you'll say delta P star is getting affected. If the pipe is inclined, instead of delta P, you'll say delta P star is getting affected. Fine, then if you have any questions, you can ask Suresh Kumar. Suresh Kumar.
Hello, sir.
Morning.
Hello, good morning, sir.
Good morning, tell me.
Sir, I have a doubt regarding flow measurement,
Okay.
discharge measurement. There you have said one problem in that you gave 10% of differential pressure is lost in the flow meter. Yes, sir. There, how you take H is equal to 10% of delta H star, but he gave differential pressure na.
See, loss over there, he gave you that the value of delta P star is equal to some 4 kilopascal in that question, if you see.
Yes, sir.
Okay. Of this 10% is lost. Of this 10% is lost. Implies pressure loss is equal to how much? Pressure loss is equal to 10% of delta P star.
Delta P star.
Imply
Yes,
head loss is equal to how much? 10% of delta P star,
P star by
divided by gamma.
Gamma. Okay, sir.
To 10% of delta H star. And that head loss is also having a formula. It is equal to delta H star multiplied to 1 minus CD square.
Yes, sir.
From there you can get this thing.
Okay, so yeah, actually pressure loss is equal to head loss into gamma. Gamma goes that side.
No, delta P star by gamma is delta H star, no, sir.
How divided by gamma can, sir?
Sir, whenever you want head, when you are having pressure, when you want head, you have to divide by gamma.
Okay, sir.
We have discussed in statics class also. Head basically
yes, sir.
Gamma.
Yes, I got it, sir.
Okay.
Thank you, sir.
Thank you. Sai Krishna.
Hello.
Hello.
Sir, am I audible, sir?
Yes, you are audible. Tell me.
Sir, I have a doubt, sir, in vortex motion. Sir, in previous IES questions, sir, there are some questions regarding this. Sir, means in those questions, sir, actually there is a vortex motion, and they are telling that at the bottom it is leaving some space of around 0.4 dia, something like that, sir. Means it is been rotated and it is leaving.
Cylinder is open or closed?
Sir?
Cylinder is open or closed?
The top is open and bottom is closed, sir.
Okay.
And at the bottom it is leaving a space of around 0.4 dia, and at the top it is having a dia around 0.9. Sir, how we have, they are asking about omega, sir. H is 0.5.
This entire height is 0.5.
Yes, sir.
Okay. Let us see this question now. This diagram is fine?
Yes, sir.
The fluid is over here. The fluid over here. So basically you're rotating with such a high velocity of omega that some bottom portion is now opening up. Now what you have to do in these kind of problems, you have to create an imaginary portion of your parabola. Imaginary portion of parabola. Let us see. This is your imaginary point, vortex point. Let us see this over here is equal to H1 and this over here is equal to H2.
Yes, sir.
You know the value of H2 minus H1 is equal to how much? 0.5 meters.
0.5 meters. Yes, sir.
Okay, the value of R1 is equal to how much for this parabola? For this parabola,
0.2
is equal to 0.2 meters. R2 is equal to how much?
0.45.
0.45 meters. Okay. Now H2 I can write as R2 square omega square by 2g, correct?
Yes, sir.
H1 I can write as R1 square
Okay.
omega square by 2g.
Yes, sir. We can solve. Yes, sir.
Okay.
Sir, and all these questions, whenever they are saying that it is leaving a gap, the same concept we have to use.
Whatever I gave you in the short notes at the end,
Yes, sir.
vortex motion,
Yes, sir.
nothing will
Yes.
come out of it. Nothing will come outside of that.
Yes, sir.
You can get a theoretical question probably, but any numerical should come within that only. For theoretical question, go for the rest of the notes. Okay,
Yes,
but
sir.
nothing beyond that. Don't worry.
Yes, sir. Sir, I have one more doubt, sir. Sir, there are some questions which are saying in IS previous, sir, which are saying sink, source, all these terms, sir. I couldn't
I'll
understand.
discuss that concept at the end. There's a particular concept called as potential flow, some 10-15 minutes concept only. Okay, some standard formula, the sink, source, vortex, doublet, uniform,
Yes, sir.
all those things. Once I finish the concept of boundary layer, I'll discuss
Yes.
it. Actually, it is a part of your kinematics only. Probably those questions are in the kinematics chapter only. But
Yes.
You'll understand at the end. The best time to understand is at the end. That is why I'll discuss it at the end. Okay, na?
Yeah. Yes, sir.
But
Okay.
very simple, only direct formula questions he'll be asking from there. Okay.
Yes, sir.
He
Yes.
asks numerical, those numericals will take at least 10-15 minutes to solve. That much is not possible. Only formula he'll ask. Okay.
Yes. Yes, sir. Thank you, sir.
Thank you, sir. Swarangi Marathe.
Hello, good morning, sir.
Tell me. Hello.
Sir, am I audible?
Yes, you are audible. Tell me.
Sorry, sir. I have still that doubt in that how to take that I in that it's center of pressure formula. Like I solved one question. In that it was given that center of pressure of a rectangular plane with height of liquid h meter from base.
Center of pressure of rectangle. Again.
Rectangular plate with height of liquid h meter from base. So I considered it as a horizontal plate.
No. Did he mention what kind of plate it is? Horizontal?
No, sir. No, sir. He didn't mention. It is volume 2 question, sir.
He should have mentioned. He should have mentioned what is the orientation of the plate. If he does not mention, generally we consider the plate in the vertical position. Standard जो है वो vertical position, because gates are always in the vertical position. These things are defined specially for gates, okay, to hold water. It is in the vertical position. Did he mention where is the plate located? How far from the interface?
H.
Can you read the entire question again, ma'am?
Yes, sir. The center of pressure of a rectangular plate with height of liquid h meter from base.
With height of liquid h meter from?
Base. I guess then some question is wrong.
Did he draw the diagram in the solution?
No, sir. It's volume 2 question, sir.
You leave that question. You go for some better questions. That is an ambiguous question now.
Okay, sir.
Okay.
Sir, in the last slide, you told that tau of that mu is related to delta P. Then does it mean that tau of viscosity is equals to tau of delta P, tau of head loss?
No. Very good. Very good. So you're saying whatever tau I got from here, that must be equal to mu into du by dy, you're asking?
Yes, sir.
No. It will be equal in the case of laminar flow. Okay. That I'll discuss actually. The topic should come later on. That is tau is equal to minus dp by dx into r by 2 is common. In laminar flow, it is going to be equal to mu into du by dy. That is correct. In turbulent, extra term called as eta into du by dy will come. Extra term will come. Okay, that we will see much later. Okay, don't worry. That
okay, sir. Thank you, sir.
Thank you. Saurav Kumar. Saurabh Kumar.
Hello. Good morning, sir.
Good morning, sir. Devin.
Sir, a transitional flow is a type of internal flow, no?
Yes, sir. It is a type of internal flow. It is basically transition from laminar to turbulent flow.
So all the equations will be valid for this also.
I told you, every internal flow, the equations are valid, whatever I have discussed, provided steady flow and fully developed flow.
And sir, what is characteristic length?
Characteristic length I have discussed in the first class itself when I defined the concept of what do you call Knudsen number. I have discussed. Remember first class? Knudsen number I discussed.
Yes, sir, you discussed, but
In
I
it,
forgot.
discussed what is characteristic. It is basic length which is defined for a particular flow. Whenever a flow is taking place, that time the primary length characteristic that flow is defined by, that is known as characteristic length. I'll give you an example. Imagine you are going to a shop to buy a pipe.
Yes, sir.
What is the first thing that the shopkeeper is going to ask you regarding the pipe? Will he ask you the length of the pipe or diameter of the pipe?
Diameter of pipe.
That's what it is, a characteristic primary length parameter.
So it is that it is governing some primary parameter or what?
It will the entire flow will be influenced by that parameter only. For example, if you are having a pipe, let us say a diameter of pipe is there, D1, okay?
Yes,
and I'm having a pipe, let us say D2. Now, no matter how much ever these, let us say D1 pipe is there, if I take this much length or I take this big length or I take this big length, whatever length I take, the value of minus dP by dx or the value of delta P by L or the value of head loss per unit length, all of them are going to be same only. All of them are going to be same. That means length is not that much important for us. In the case of pipe system, length is not that much important for us. Cross-section area is very important for us. For example, the moment I change the diameter, automatically everything will change. Everything will change. The flow can even change for laminar to turbulent also. Are you following?
Yes, sir.
So over here, who plays more important role, diameter or length?
Diameter.
Diameter. It is a character. That is basically the defining parameter over here. Okay.
And so what for rectangular?
Rectangle, again, cross section is important. अब rectangle में cross section is important. उस cross section में we are basically trying to convert a rectangular cross section into its effective circular cross section. Its effective circular cross section is going to have a diameter. That diameter is called as your hydraulic diameter. So we are having a rectangular cross section. उसको हम we are imagining what is the effective circle for that. That effective circle is having hydraulic diameter. Do one thing. You find out the value of hydraulic diameter for circle. You will see hydraulic diameter for circle. Check once. It will become equal to D again. So basically the idea of hydraulic diameter is convert any kind of cross section into its corresponding circular cross section. That will give you some diameter.
Okay, sir. Okay, sir.
Thank you.
Thank you.
Saurav Kumar.
Hello, good morning, sir.
Good morning, sir. Tell me.
Sir, एक गेट का क्वेश्चन है सर 1999 का. Sir, in a steady radial flow into an intake, the velocity is found to vary as 1 upon r square.
One second. Where velocity
is found to vary as.
Okay. R is proportional to 1 upon r square.
Yes, sir.
Okay. Next.
The acceleration is proportional to
1 by r power how much? 5 answer. Let us see.
Oh, yes, sir. Yes, sir.
Let us say VR. This is civil question, I think, na?
Yes, sir.
Let us say VR is equal to C upon r square.
Yes, sir.
Okay. What is AR formula? AR formula क्या है? It is equal to dou VR by dou T plus VR into dou VR by dou R plus V theta by R into dou VR by dou plus Vz into dou VR by dou Z. And finally, you're having minus
V square, V theta square upon R. Yes, sir.
Now you see this VR over here is a function purely of R. किसी और का function है? अगर ये function केवल R का है, if it is a function purely of R, every other thing will get cancelled off. V theta is not defined, therefore V theta is also getting cancelled out. अगर V theta define होता तो V theta को रखते हम, लेकिन V theta define नहीं है यहाँ पे. अब बस इतना टर्म बच गया. तो क्या बन गया? ये तो बन गया C upon R square.
Yes sir, yes sir, got it. Yes sir.
Very good.
ये 1 upon R cube. Yes.
Now tell me how many marks this question is for?
1 mark sir.
1 mark. Now you see this question, it won't even take 2 minutes in examination. I'm telling you, in civil examination, only formulas are going to be important. Okay.
Yes sir.
The form I am telling you, kinematics, पूरा kinematics कर लीजिए आप previous gate का civil में. सिर्फ फॉर्मूला काफी है सारे आंसर निकालने के लिए. ठीक है ना?
ये सर कर गेट का क्वेश्चन हो गया सर, तो बस वो ईएससी का क्वेश्चन अब जाना पड़ेगा.
ईएससी के क्वेश्चंस के अंदर एम्बिग्यूटी हमेशा रहेगी, याद रखिए इसको, क्योंकि ईएससी क्लियर करते जाएगा. आप जितने ज्यादा क्वेश्चन प्रैक्टिस करते जाएंगे, आपको क्लैरिटी ज्यादा बढ़ती जाएगी. ठीक है ना?
यस सर. ओके, थैंक यू सर.
थैंक यू. साई महेश कोटिवाड़ा.
Hello sir.
One minute. Tell me please. You keep telling.
Sir, in launch sprinkler questions, while writing equation of torque, why we are taking the direction of torque in the direction of V1 and V2, sir?
This is why.